Hello everyone. Today we'll be going over mostly the project for specs and how you can analyze different parts of the project. So to help you understand what the spec explains and how you can implement the project more efficiently without any doubts. And before going into detail of the specs and the project, I'll be going over this one slide about the power and energy management in software using real-time scheduling techniques to reduce the power consumption in software itself by putting the microprocessor, when it is not doing any work, putting it to sleep or in halt or stop mode. And that can be easily done by use of various instructions that are present using the APIs. So let's look at one example. So this is an example of a real-time, run-to-completion scheduler in which you have in which a scheduler can execute a stop or a halt instruction when it has no tasks to run. And when there is an ISR or anything becomes ready, the CPU can come out of that halt or stop state and start executing normally in a normal condition. So if you look here, you have a while one loop for the scheduler which goes through the scheduler table and executes whatever tasks that are ready. And if you look in the for loop, so there is no code depicted right now, but it just shows that the for loop will traverse through the task list and then decide which task to run. And if there are no tasks to run, it will come out of the for loop. And if the halt feature is enabled, it will put the process into halt mode, or it will put it into stop mode. So those are two different features based on what peripherals would be turned off, which clocks would be gated to reduce power consumption, and stop mode would disable most of the clocks and a lot of the peripherals, whereas the halt mode would have more flexibility in terms of power saving. It won't put everything to sleep. It will only reduce the power consumption of the processor and some of the peripherals, and when any of the ISRs are triggered, it will come out of the mode and start executing the loop back again. So that is just to give you an idea that the scheduler and the IL78 is capable of going into the halt or stop mode, and you can extract those, you can exploit those features for optimization. So that was mainly it, and then we can dive into the project specs, and I'll walk through it and explain and demonstrate how you can either modify the board or and walk through the code to assess how your code is performing. So, okay, that's not a good idea. Okay, so as you're all aware, there are two parts to this project. One part is for ECE 461 students and 561 students, and the second part is for ECE 561 students only. So I'll be going over both the parts. First, I'll discuss what part one is, what part one specifies. So in part one, you're supposed to optimize the code that you had in project 3 and drive the board through a ultra capacitor instead of the USB power, and monitor the voltage as it drops using the dial that you had designed in project 3. So in order to do that, so the output should look something like this, in which you have the dial and the needle and the stopwatch, which monitors the time and the time so far elapsed when you. So you can restart that watch based on a switch. That is also mentioned in the spec. So whenever you press the switch, it should reset it, and you can start the watch anytime and monitor the voltage as it drops when you're driving the board through an ultra capacitor. And to give you an idea, so the relationship between the power maintenance unit is given by the formula up there, and the time it takes for the voltage to drop between the two voltage levels for an ideal circuit is given by the second equation, which is T is equal to C, the capacitance, times the difference in voltage levels that you are observing, and divided by the current being consumed during that time. But if it's taking the resistance into account, it won't be an ideal circuit, so you'll have some time delay, and the capacitor discharge will be proportional to the resistance as well. So there's that formula, and let's see. Okay, so the requirements on the specs are that you should be updating the LCD every 100 milliseconds. So instead of updating it every time the voltage is changing, you will be calling an update function or subroutine, which will be updating the dial and the stopwatch every 100 milliseconds instead of every time the voltage changes. So that would avoid consuming too much power when you are calculating the voltage and other things. So you are also required to enable a switch in which when you press the switch, the stopwatch should reset and start counting, so that you don't have to reflash or restart the entire program every time you want to monitor the voltage. So what you could simply do is have this ultra cap charged and then connect it and just press the reset button so that you can monitor the time and the voltage straight away without having to reconfigure the or restart the entire board. Okay, so that's one part. Let's see. Okay, so now the way you'll be monitoring the voltage is by monitoring the 3.3 voltage rail on the board, which is initially, so what you need, so instead of, so when you know you're powering the board through the ultra capacitor, the voltage will keep on dropping. So the reference voltage for the ADC will drop as well. So if you try to monitor any other voltage with respect to the voltage rail, that will be ideally corrupted. So that is why you're required to monitor the voltage rail itself and have a reference voltage set to another source, which is, I forgot the exact part, but it's 1.5 volts, which is 1.45 volts. So that voltage will be fixed irrespective of what the supply voltage is. As long as the supply voltage is above 1.6 volts, that 1.5 will be constant. So that is why you see a difference or a change in the formula. Normally you have V in of the ADC divided by the V reference voltage. That is how you calculate the actual voltage in the ADC. But instead of having that, you will be calculating you have 1.45, which is the input to the ADC, as a constant voltage, and the reference voltage will be changing as the ultra cap would discharge. So that is why you have the V3 in the denominator, which is the reference voltage. And using this formula, you can actually, this is sort of an inverse of the original formula for calculating the voltage from an ADC input. So what you're basically doing is, instead of having a reference voltage and looking at the ADC reading to calculate the ADC input voltage, you are having a constant input voltage at the ADC input and variable reference voltage to calculate how that reference voltage is changing to determine how much the voltage rate drop is. So that is why the inverse in the formula. So, Dr. Yvonne, yes.
Right. So the ADISS flag up there is actually a bit in the ADS register, but the C compiler support doesn't specify that flag. So you need to set that, and what you need to do is look at the hardware manual, and page 628 covers how you set that register. But the ADS register actually has the most significant bit being that ADISS bit. So essentially you're going to need to take the channel you want and OR it with 128.
Okay. So I'll repeat that for everyone once again. So what Dr. Dean is saying is that the ADISS is the most significant bit in the register ADS, but the compiler doesn't allow you to use that variable ADISS to set that bit. So what you would want to do is set ADS as 1, which is representing channel 1, and look up in the hardware manual to locate the ADISS bit and OR it with the registered ADS to get to set the most significant bit to 1. So yeah, if you have any questions about that, you can contact me or Dr. Dean later. And there are a few suggestions to improve your performance and make the UltraCap last longer without consuming too much power. To reduce the current consumption, so you can turn off a lot of the MCU peripherals, which you won't be using, like the serial communication and other peripherals like potentiometer, the audio, the Wi-Fi module, and stuff like that. Do not and you can also disconnect various LEDs, which are status LEDs, which you won't need, and they keep flashing, so you can get rid of those. And you can obviously exploit, as I mentioned earlier, the halt and stop modes when you're not doing any work. You can speed up the SPI communications so that the SPI module does not consume power for a longer duration, and you can turn it off. You can transfer all the data together at once and not transfer in small packages. And you can also adjust the LCD settings by reducing the brightness and lowering the voltage as well. And again, you can also lower the voltage in the MCU to perform the same task while maintaining the minimum voltage. So let's see. These are a few of the references. So now the important part. Yes.
One other thing is, thank you for coming to class on the last day and not going to senior design. One of the switches on the dip switch will turn off power to the Wi-Fi module, and that'll save you 10 milliamps or so. So, congratulations. Give it a try.
So yes,
It makes a big difference.
Yeah, look at one of the DIP switches to turn on the Wi-Fi module. Okay, so now the UltraCap can be connected in various ways. So it doesn't really matter where you connect it as long as it's on the 3.3 volt rail. And one thing to remember is that it is polarized. So the silver line on the side of the UltraCap represents the negative terminal, and you should connect that to ground, and the other one to the positive terminal of the voltage rail. So let's see. So I can show you where these places are located on the board. Help you find where you can connect it. So one way is to so the thickness of the UltraCap and the spacing between the two pins is not too wide, so you might have to solder or connect some sort of wires to the leads to connect to any of the locations that you wish to connect the UltraCap to the board to. And you can look at a few locations here.